All right, so we are going to start with a warm-up, and our warm-up is to multiply using FOIL. So if you recall, FOIL stands for first, outer, inner, last. So in order to FOIL, you're going to take the first two terms of the binomials and multiply those together. So upon multiplying the first two terms, we have x times x, which gives me x squared. And then you're going to multiply the outer two terms together, which is negative 2x. The inner two terms multiplied together gives you a positive 2x. And the last two terms multiplied together is a negative 2 times a positive 2, which is a negative 4. And then our last step of FOIL is to combine like terms. So in here we can see negative 2x and positive 2x are like terms. So when I combine those like terms together, they actually cancel each other out because they're additive inverses. So this simplifies or reduces to x squared minus 4. In example B, we can see that this one looks very similar to example A. So in example A, we had x plus 2, x minus 2. In example B, we have 4x plus 5 and 4x minus 5. So we're going to follow our steps for FOIL once again. So you get 16x squared outside gives you negative 20x. Inside gives you positive 20x. And then positive 5 times negative 5 is negative 25. Once again, combining like terms, we notice that negative 20x and positive 20x are additive inverses, so they cancel each other out. And we're left with 16x squared minus 25. So today we are on part 2 of factoring quadratics, and today you will be able to solve quadratics by using two special formulas. One of those formulas is called the difference of squares, and the second formula is called a perfect square trinomial. In the previous example, our answers upon FOILing gave us two examples of difference of squares. So difference means subtracting, and squares are perfect squares. So our perfect squares are 1, 4, 9, 16, 25, 36, etc., etc. And in terms of variables, that's x squared, x to the 4th, x to the 6th, and so on. So a difference of squares is a set of binomials that consists of two perfect squares being subtracted from each other. A difference of squares can be factored in one of two ways, as a minus b times quantity a plus b, or quantity a plus b, a minus b. The order does not matter, meaning where I put the negative and the positive doesn't matter. As long as I have one negative and one positive, and a and b represent the square roots of a squared and b squared. When factoring using a difference of squares, there are a few things we want to look for in a problem to identify it as a difference of squares formula. One of the things we're looking for are two terms. The next thing we want to look for is a minus sign between the terms. And the final thing we want to look for is that both terms are positive squares. meaning that, or not positive, sorry, perfect squares, meaning that both terms fit into that pattern of x squared, x to the fourth, x to the sixth, and so on, and have coefficients of 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225. And I could keep going, but I won't bore you with all of the perfect squares. However, you do need to always look for a GCF. Sometimes you have a hidden 2 or 3 being multiplied in, and we have to divide by that 2 or 3 to get to those perfect squares. So anytime we're factoring, we are always looking for a GCF, which is why we learn GCF before we learn our formulas and our other factoring techniques. So we have x squared minus 16, and we're asked to factor this. So this is a case of a difference of squares. X squared is a perfect square, 16 is a perfect square, and we have a minus sign between them, which means that this factors as x minus 4, x plus 4. Similarly, in our next example, we have x squared minus 49. So x squared is a perfect square, 49 is a perfect square. We apply our formula. The square root of x squared is x. The square root of 49 is 7. So we get x minus 7, x plus 7. Similarly, for x squared minus 1, 4 is a perfect square. X squared is a perfect square. So you can have two perfect squared multiplied together and still apply our formula. So the square root of 4 is 2. Square root of x squared is x. So we get 2x. 1 is a perfect square. So you have 2x minus 1, 2x plus 1. And you can always do a quick check backwards to see if it foils back into what it was. Okay, 36x squared minus 81. So here 36 is a perfect square, 81 is a perfect square. So we apply our difference of squares formula, and you have 6x minus 9 and 6x plus 9. Our second technique is a perfect square trinomial. A perfect square trinomial is the product you obtain when you square a binomial with a perfect square at the beginning and the end in our trinomial formula. So a trinomial will look like a squared plus 2ab plus b squared. If you have plus plus, it's a plus in the middle. If you have a squared minus 2ab plus b squared, then it's a minus in the middle. A squared and b squared must be perfect squares, and the middle binomial term is 2 times the square root of a and the square root of b squared. When factoring using perfect square trinomials, we're going to look for 3 things. You need to have 3 terms. The last term must be positive, and that's really important, as well as the first and the last terms must both be perfect squares. And then if all 3 of those are true, we have kind of this conditional that says the middle term has to be 2 times the square root. of a and b squared. So for example, we have x squared plus 8x plus 16. So x squared is a perfect square. 16 is a perfect square. The square root of 16 is 4. The square root of x squared is x. So you have 4x times 2, which is in fact 8x. So I have 3 terms. The last term is positive. The first and last terms are perfect squares. And 2 times both of their square roots is in fact the middle term. So what that means is this factors as x plus 4 times x plus 4, or as x plus 4 squared. So first step, look at how many terms. 3. Is last term positive? Yes. First term a perfect square? Yes. Second term, or last term rather, a perfect square? Yes. Is the middle term 2 times the square root of the other terms? So that would be like 2 times 2x, which is the square root of the first term, times 3, which is the square root of the last term. So 2 times 2 is 4, 4 times 3 is 12, 12 times x is 12x. So it fits our requirement. So that means this factors as quantity 2x plus 3 times quantity 2x plus 3, or 2x plus 3 squared. Perfect square, 3 terms, positive at the end. Positive here tells me both factors are positive. And let's check to see if the middle term matches. So square root of 25 is 5, square root of x squared is x, square root of 81 is 9. So 5 times 9 is 45. 45 times 2 is in fact 90. So then this becomes 5x plus 9 squared. 100's a perfect square, x squared's a perfect square, 81's a perfect square. 3 terms, positive at the end. So let's see, square root of 100 is 10. Square root of x squared's x. Square root of 9, or square root of 81 is 9. So 9 times 10 is 90. 90 times 2 is in fact 180. So we have another perfect square trinomial. So it's 10x plus 9 squared. And if that was a minus between the 100x squared and the 180x, then this would be 10x minus 9 squared. So here's a case where we do have that minus. 64 is a perfect square. X squared is a perfect square. 1's a perfect square. Positive at the end. So 2 times 8x times 1. Two times 8 is 16. 16 times 1 is 16, which is not negative 14x. So this is not an example of a perfect square trinomial. And there are no factors in which we can factor this nicely. So this is a case of either a prime or a technique we just don't know yet. So we are going to list that as prime. So for your homework today, I'd like you to do that next page in your notes packet that says 5-3 special formulas, one's difference of squares, and then the next page is trinomials, and I'm going to put those up for you so you can see them. So 1 second. So for practice, you're doing the 5-3 factoring a difference of squares and perfect square trinomials homework. So that is 1 through 15. 1 through 15 on that worksheet page.